What is a quantum internet? A quantum internet provides radically new internet technology that allows us to solve tasks which are impossible to accomplish on the classical internet. As with any radically new technology, we cannot yet foresee all applications of a quantum internet, but it already has quite a number of exciting ones. For example, it allows us to do absolutely secure communication, secure identification, position verification, secure dedicated quantum computing in the cloud, and many others we will visit in other videos. So what does a quantum internet look like? On a quantum internet, we don't send classical bits, zeros and ones, but we will transmit qubits. But otherwise, the basic elements of a quantum internet do not look so different from the classical one. The first element of a quantum internet is what we call an end node. An end node is basically your computer or laptop or phone that is attached to the internet and that you use in order to run applications. So you need the end node in order to use the quantum internet. As the name suggests, on a quantum internet, we will not use normal laptops, cell phones or computers, but instead we will use quantum computers. These quantum computers actually don't need to be very complicated. It turns out that most applications of a quantum internet only require these end nodes, quantum computers, to be very simple and have less than 10 qubits. In fact, for most applications, they only need to have 1 qubit. The reason why we typically do not need many qubits is because a quantum internet draws its power from quantum entanglement. And already 1 qubit at each endpoint is sufficient to have entanglement. In contrast, on a quantum computer, we always need more qubits than can be simulated on a classical computer in order to do something new and interesting. The next element of a quantum internet is that, similar to the classical internet, we have all kinds of elements that allow us to maximize the use of existing infrastructure. On a classical internet, not every computer on the internet has a direct fiber connection to every other computer on the internet. But instead, fibers run through central points, where there are switches that direct the bits in the right direction. If you want to build a quantum internet, then similar to a classical internet, you, for example, want switches that are capable of switching single qubits. Now, ideally, we would like to send qubits over very long distances, from any point on Earth to any other point on Earth. In order to achieve this, we will need something that is capable of sending qubits over long distances. This requires a very special form of repeater called a quantum repeater. A quantum repeater works very differently than a classical repeater. And in the separate video, you will learn all about quantum repeaters. When realizing a quantum internet, then just like on the classical internet, we will also need some control traffic. Basically, next to the quantum communication, we will also use classical communication, for example, to direct the qubits to the right destination in the network. This is what a quantum internet looks like. Now, I've already mentioned that a quantum internet allows us to solve tasks that are impossible to accomplish on a classical internet. Now the question is, what makes a quantum internet or what makes the transmission of qubits so much more powerful than what we have today. Qubits have very special features. For example, they cannot be copied, making them ideal for security applications. 2 qubits can also be in a very special state, namely an entangled state. An entangled state between 2 qubits is the essence of the power of a quantum internet. In order to understand entanglement, or why entanglement is so useful, it is sufficient to understand 2 very fundamental properties of entanglement. So let me explain these 2 properties of entanglement and why they give power to a quantum internet. The first feature of entanglement is that it allows maximum coordination. So what does this mean? 2 qubits can be entangled even at very long distances. For example, I can have a qubit in Delft, which is entangled with a qubit very far away, for example in China. Now, if I make a measurement on my qubit here in Delft, and a friend of mine would make the same measurement in China, then it will turn out that we always get the same outcome. You can think of a measurement as asking a question to a qubit. For example, I might ask the qubit, are you pointing left or are you pointing right? Maximum coordination means that if I see the outcome left in Delft, then immediately, instantaneously, if my friend in China makes the same measurement, the qubit will also be pointing to the left. And if I see it pointing to the right, then also in China it will be pointing to the right, even if this answer is not determined ahead of time. In fact, randomly, we will get left-left or right-right, but the point is that the outcomes will always be the same. And the amazing thing about entanglement is that this is true for any measurement or any question we might ask. If I were to ask the qubit, "Qubit, are you red or blue?" then we would always observe maximum coordination. Red-red or blue-blue, but never anything else. So the first feature of entanglement is maximum coordination. And it is this feature that makes entanglement so suitable for tasks that require synchronization or coordination. The second feature of entanglement is that it's inherently private. Because of course, you might have been wondering, given that entanglement is so powerful, allowing this instantaneous maximum coordination, wouldn't it be great if many qubits could be entangled? Now it turns out that only 2 qubits can be maximally entangled with each other. So entanglement is inherently private. If I have a qubit here in Delft, and the qubit that it's entangled with is somewhere in China, then you can think of this entanglement as a private connection that nothing else can have part of. It is not possible for any other qubit anywhere to have any share of this entanglement between the Delft qubit and the qubit in China. It is this feature that makes quantum communication so fundamentally suitable for tasks that require privacy and security. So entanglement gives power to a quantum internet. And in a later video, we will see how to use this entanglement to also send qubits using quantum teleportation.